Good afternoon. Today I'm going to be talking a bit about some computational approaches to the GIT for complete intersections. And to begin with, I will be talking a bit about I'll be giving a brief background on the GIT. Um, so the main goal of the GIT is to describe quotients of varieties with algebraic group actions. And this was initially started by David Hilbert, but his approach was a bit flawed because it relied a lot on finding invariants on these varieties, which is quite hard. And David Montfort in the 60s circumvented with this below approach. So the setting for this description is essentially having a projective variety X over a field K, a reductive group G, and a line bundle L of X. And to define the ring of X as usual, and similarly to define the ring of invariants with respect to G, which is defined in a similar way, but we only need the invariant elements of the ring of X under the action of G. This is, for reductive groups, this is a finitely generated ring, which helps a lot with the theory, and it allows us to obtain an induced rational map between X and this quotient, which is X slash G, which is defined as the proj of the invariant ring, which, although is defined as not a morphism, because for some specific values of f, these are all zero for every x for some specific values of x. To circumvent that, we define these points which we call semi-stable points, and these are points in X where there exist some sections with respect to the line bundle L for some M, such that the section at X is non-zero. And this allows for the restriction of this map, this induced rational map phi, to be a categorical quotient. In a similar way, we define the stable points of X as the semi-stable points with closed orbits and finite stabilizers. And the restriction of this map phi to the image of phi of the stable points is in fact the geometric quotient, which is noted again as X quotient G. And because of this description, essentially the goal of the GIT is shifting the task of it, essentially shifting to describe these loci, these stable, semi-stable, and polystable points, where polystable points are the closed orbits. So in order to do that, it would be very hard if we didn't have something called the Hilbert-Montfort numerical criterion. But thankfully we do, and this is the following description. So we define some group homomorphisms. These are usually defined by lambda, and these go from this torus GM to the group G. And these are also these are called one-parameter subgroups. And the one-parameter subgroups essentially, because of the action of G on X, it also induces an action of GM on X via the one-parameter subgroups. Essentially, we have this action being X going to lambda T acting on X, where lambda T obviously is an element of G, and T is an element of the torus. And the Hilbert-Montfort numerical criterion reads as follows. So a point in X is semi-stable if and only if the limit as T goes to 0 of this lambda T acting on X is non-zero for all one-parameter subgroups. In a similar way, a point X is stable if and only if this limit does not exist for all one-parameter subgroups. Then this makes the study of the GIT much more easier to find these stable and semi-stable points. A bit of notation: we denote these categorical quotients by new GIT, and we denote the geometric quotients by new bar GIT, which in fact are moduli spaces, which in fact proves the usefulness of GIT, because through GIT we can actually study these moduli spaces and construct them. But in reality, studying all of the above isn't very easy. So the natural question and motivation is essentially, if we can study the above computationally and find computational methods to study these quotients in order to get more concrete results. So the current progress for this has been done in 2018, where Gallardo and Martinez Garcia in their study of a generalization of GIT called variational GIT of log pairs of hypersurfaces of degree D alongside with a hyperplane section in Pn+1. They studied these GIT quotients under SLN+2 action computationally. And the restricted quotient, like the simplest case of the quotient, which is essentially this, as you see here, where the left-hand side it can be recognized as Pn for some specific n, and obviously the group acting is SLN+2. In studying these quotients, they found two, in the simplified setting, at least they found two results. And the main two results is, which we denote by theorem 1. And in theorem 1 reads that essentially you have a finite set, an explicit finite set, S and D of one parameter subgroups, such as the hypersurface X of degree D is not stable or not semi-stable if and only if for some G in the target group, the Hilbert-Monfort numerical criterion fails for G acting on X for some lambda. This is useful because if you remember, the Hilbert-Monfort numerical criterion essentially requires us to check if something is stable through all one parameter subgroups, but this essentially tells us that if we want to check if something is not stable, we can check a finite set of these one parameter subgroups. And based on this, we found that in this theorem 2 that there exist these sets, NO plus lambda and N plus lambda, where lambda is in S and D, such as the hypersurface of degree D is not stable if for some G in SLN+2, the set of monomials of G acting on X is contained in one of these two sets. This is based on some work done by Monfort, but for some similar cases, but essentially what differentiates from this is it's a much more concrete computational approach. And in fact, they developed actually a Python code for this that can construct the above three sets for arbitrary N and D. The natural question is if this method can be extended for other GIT quotients and in specific cases where the G scheme is not Pn. And the motivation for this comes for this. If we can consider the common vanishing locus of K homogeneous polynomials of degree D, which we know by F1 up to Fk in Z in Pn, here you can see how the variety arises X. Can we study this computationally? And we study usually these intersections, these complete intersections through the Grassmannian. So essentially, we want to study the GIT quotient between the Grassmannian and the SLN+1 reductive group, which is a natural reductive group for this action. Focusing on our analysis of the Hilbert-Monfort numerical criterion, we can extend in some way the theorems 1 and 2 for the complete intersections. And in fact, we find the following. So there exists, again, an explicit finite set. This time we denote this by P, depending on N, K, and D of these one parameter subgroups, such that the variety obtained as the complete dissection of these K hypersurfaces of degree D is not semi-stable or not stable if for some G in the target group, the Hilbert-Monfort numerical criterion fails for G acting on X for some of these lambdas. In a similar way, there exists K tuples of sets, these NO minus and N minus of this very complicated things where every X to II is a monomial of degree D and lambda belongs to the set above, such as the variety obtained as a complete dissection of these K degree D hypersurfaces of degree D is not stable or not semi-stable if for some G in the target group, the set of monomials of G acting on X is contained in these two sets. These xi are all support or flag monomials of degree D. It's a kind of like a convention to denote them this way. It's easier than writing this whole thing. And it's useful to note that these sets NO minus and N minus are in fact maximal with respect to a total order on the monomials of degree D. And in a similar way to Gallardo and Martinez-Garcia, we have developed a program in SageMath that can find the set P and KD and the K tuples of sets NO minus and N minus for arbitrary values of N, D, and K. The thing is, though, that the description of these sets is much more complex than their counterparts for k equals 1. So this, although it's a useful method and it gives some computational results, it has a heavy constraint because even for small, for not so large values of n, d, and k, we obtain a problem. Not usually a problem, but the program slows down significantly, and it's kind of hard to obtain computational values for large values of n, d, and k because of the amount of time the program needs to take. That's all I wanted to say. Thank you very much. I hope you enjoyed this talk.